Your model got worse, but drift alarms alone do not tell you why. I'll separate covariate shift from concept drift in Python, so you know what to fix first. This is the pattern you'll be able to implement by the end, which sets a reference baseline and diagnoses whether production shows covariate or concept drift. I'm Professor Pi, teaching AI foundations with simple Python. Models in production stop being an academic toy the moment data pipelines change. A classifier trained on tidy examples can still fail quietly when upstream systems alter inputs, or when the real world changes how labels are generated. Success here means you not only notice performance loss, but you also know whether to fix the inputs or retrain the model. Practitioners reach for simple, reproducible checks because they scale and explain action to engineers and stakeholders. At a high level, covariate shift means the inputs moved, but the label rule stayed the same. Concept drift means the mapping from inputs to labels changed, while inputs look familiar. A toy example helps. Imagine a two-feature sensor stream. If sensor calibration drifts, feature means shift and your model misfires. If someone changes the sign of a rule that decides labels, the features remain the same, but model predictions go wrong. We will build a small diagnostic pattern. First, we set a baseline accuracy on held-out validation data. Then, we simulate an input change and a mapping change. We run simple statistical checks on features and compare accuracy drops. The logic recommends whether to inspect the data pipeline or retrain the model, and it keeps decisions clear for engineering teams. Now we will train a baseline classifier and record a reference accuracy. This snippet trains a baseline classifier in scikit-learn and records a reference accuracy to compare against production. A reproducible random generator creates small Gaussian feature matrices for train and validation. The variable W defines a simple linear rule, and we add Gaussian noise before thresholding to produce labels. Logistic regression fits to the training inputs and labels, and accuracy score evaluates predictions on the validation set. The max iter setting controls solver convergence. Increasing it can help if you see warnings, but it rarely changes accuracy here. The printed baseline accuracy anchors how well the model performs before any drift shows up. Next, we will simulate a batch where the input distribution shifts, but the labeling rule stays unchanged. This example simulates a covariate shift where feature distributions move, but the label rule stays the same. We draw a new Gaussian batch, then shift x1's mean and scale x2 to mimic upstream pipeline changes. The label y-cov still follows the original linear rule using the same weight vector, so the conditional probability of y given x is unchanged. We evaluate the existing model on this shifted batch using an accuracy score, and we summarize input changes with a pandas data frame that prints feature means. If you increase the shift magnitude, mean x1 or mean x2 move further, and accuracy may degrade more. The printed values show both input shift and its immediate impact on accuracy. Now, we will run a simple statistical test on each feature to detect distribution change. This code quantifies feature drift by applying SciPy's KS2 sample test to each feature. We compare the validation reference features to the covariate shifted batch, column by column. The KS2 sample test returns a p-value for the null hypothesis that both samples come from the same distribution. Smaller numbers indicate stronger evidence of drift. We round the p-values for quick readability and print them as a compact list. With larger sample sizes, the KS test becomes more sensitive to subtle shifts. With fewer samples, only big changes trigger small p-values. The printed p-values tell you whether input distributions changed enough to be statistically detectable. Next, we simulate a batch where the label rule changes, but the input distribution stays similar. This snippet simulates concept drift by changing the relationship between features and labels while keeping the feature distribution similar. We sample a new batch from the same Gaussian as validation, but we alter the label rule by flipping the sign on the first feature in the linear rule, so the conditional distribution of y given x changes. The existing scikit-learn model predicts on this batch, and the accuracy score measures the performance drop relative to the baseline. Because the input distribution did not move, a feature-only drift test like the KS2 sample test would not flag this, yet the accuracy declines. If you increase the magnitude of the rule change, the accuracy falls further. The printed accuracy highlights how concept drift breaks the original mapping, not the inputs. Now, we will combine signals into a simple decision rule that recommends what to do next. This example turns the signals into a simple decision: which failure mode is most likely and what to do next. We compute the minimum KSP value across features to flag input drift, then calculate accuracy drops versus baseline for the covariate shifted and concept drift batches. A small rule set assigns an action. A large accuracy drop with no feature drift, or a much larger drop in the concept case, points to concept drift. A large drop with feature drift points to covariate shift. Otherwise, keep monitoring. Tightening the thresholds catches subtler changes, but may overreact. Loosening them reduces false alarms. The printed diagnosis summarizes the next step you should take. In a real project, this toy mapping becomes a monitoring service. You would register baseline metrics, run the KS test on live feature windows, track accuracy on sampled labels, and trigger pipelines that either roll back data changes or kick off retraining. The same logic scales to more features and more complex models, though you will tune statistical windows and thresholds in practice. Recap: covariate shift is when inputs change, but the label rule stays the same. Use feature distribution tests plus accuracy checks to diagnose it. Concept drift is when the mapping from inputs to labels changes while feature stats look stable, and it usually requires model updates or relabeling. Caveat: statistical tests are sensitive to sample size and threshold choices, so treat alarms as prompts to investigate, not as blind commands. Next step: tune the decision thresholds and the statistical window size for the KS test. Try wider windows for stable sensors and tighter windows for fast-moving streams, and measure how often you want alerts versus false positives. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.